Okay. So let's move on to converting. We learned last time how to go from binary to decimal. So let's make sure that we can go in the other direction, right? So that'll be in the next section in your book. And let's say I have a number 23, all right? And I ask you to take that decimal number and convert it to binary, all right? So we're just going to do the reverse of what we did a minute ago, where it's probably, I would just kind of make some spaces here. And when you do this enough, you start remembering what the numbers are, right? It's 1, 2, 4, 8, 16, 32. So basically you want to go up to the biggest number that you have here that's also smaller than this number here, right? So like in the case of this one, 1, 2, 4, 8, 16. If I go up another one, I'm going to hit 32, which is bigger than 23. So I don't need that one. You could put it there, but you're going to end up having zeros on those, right? So the way that this one works is you start by putting a 1 at the biggest number that's less than 23, which in this case would be 16. And then you think, what's the biggest number I can add to 16 and not go over 23? Well, if I add an 8, what number do I have?
24.
24. So that's too big, right? So I can't do 8. So I'm going to put a 0 there, but I can do 4. 16 and 4 is 20. So what's the next biggest number I can add without one going over? I can add the 2. That puts me at 22, and then I'll put a 1 at the 1. Now I'm at 23. Right? So I can add all that up here to make sure that I got it right. 16 plus 4 plus 2 plus 1. I can enter that in my calculator if I want to, whatever, and just make sure that the number I get is 23. So this would be my answer when I'm converting from that decimal number to binary. Any questions about how I did that? Does anybody need to see another example, or you think you got that down? Who wants to see one more? One more? Okay, all right. So we'll do a little bit bigger number. Let's do 73. All right. So 73, I know, again, the way that these go up, 16, 32, then 64, and then from there it's going to go 128. That one's going to be too big. So I'm going to start with the 64, right? So I've got 64, 32, 16, 8, 4, 2, 1. And so I'm not going to have a 1 here. So there's going to be a 64. 64 plus 32. That's way too big, right? That's 96. So I've gone over if I do that. What about 64 plus 16? What does that give me? 80. So I'm still too big with that, right? So let's put a 0 there. 64 plus 8 is 72. That's actually really close. So 72, I know only need one more to get to 73. So I'm just going to put a 1 here. And 0 is right there. All right, so again, I'm going to check my work by adding them all up. 64 plus 8 plus 1. 64 plus 8 is 72 plus 1 is 73. So sure enough, I get 73. Okay? Yes?
So you're basically just like going from the end number and then putting either a 1 or a 0, whichever one you want to add to that to get the number that you're trying to get, either it was 23 or 73?
That's right. Okay. Yeah, just can't go over the number, right? So that's how I decide whether I'm going to put a 1 there or not. If by adding a 1 there puts me over the number, then I don't want to put a 1 there. But I need to start I got to make sure that I start at the right place, right? That I start with the biggest number that's below this one. Okay? Any other questions? All right, let's talk about hexadecimal numbers then. If decimal is the base 10 number system, decimal is base 10, which makes sense because of this prefix there. A decathlon is an event. It's 10 events, right? A decade is 10 years. So the deci meaning 10, base 10, binary, the bi prefix meaning 2. So this is base 2. What do you think a hexadecimal with a number, like with a prefix of hexa might be? Yes?
Like 16.
It is 16. Is that what you would think? I tend to think of 6 with hex, right? So our hexagon is 6-sided, so it's a little bit, don't let that trip you up, right? And think that this is base 6. It's actually base 16. So let's talk about the base 16 number system. Since it's 16, then it means that it's got to have 16 digits in it. Well, we've got a problem since we live in a decimal world, right? What's our problem?
We only have 10 numbers.
We only have 10 numbers to work with, right? So that's not, we're not going to be able to just use the 10 numbers. So how do they account for the additional 6 numbers that we need? Well, they start with the alphabet. Yes? Yes.
I think they add letters.
They add letters. That's exactly right. So A through F is what we do to add on to those 16. So it basically goes 0 through 9, and then when you get to 9, you go A through F, right? That's how you do hexadecimal numbers. And just to kind of, if we were to build a table to kind of lay those out, and I'm not going to do all of them, but we could put a column here for the decimal number, and a column here for the hexadecimal number, and then a column for the binary equivalent to it. So if I start with 0, so if I start with the decimal number 0, the hexadecimal equivalent is 0. The binary equivalent, I'm going to do it because it's going to take 4 binary numbers to go all the way to 16. I'm going to put 4 zeros here. All right. So if I go 1, 2, 3, these are all going to be the same all the way up to that, right? The binary is going to be 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. That's how we would represent each of those guys. It reaches a point when you've done this enough that you just kind of know what order to change the ones on, right? But if we had to, we could do the conversion, right? We could see here that this is the ones place, so that would be a 1. This is the twos place, so that's the only place we would have a 1 there. If we wanted to make the decimal number 3, we would have a 1 in the twos place and a 1 in the ones place, because 2 plus 1 is 3, right? And so they kind of look the same all the way down until you get to until you get down here to basically where 10 is, right? So when we hit 10, I think I'm going to have to add another row. Let's see, 10, 11, 12, 13, 14, 2 more rows. 15, 16. So when we get to 10, now we've got bigger than the 9 that as we were going down in the decimal. So this is where we start with the letter A, B, C, D, E. Oh, wait a minute. Sorry. I didn't need an extra row because we don't actually go all the way to 16 because we started with 0. So that gives us a total of 16. And for this guy, let's see, what would 10 be in binary? It would be a 1, and then 1, 0, 1, 0, right? In the 8 place, and then the 2 place, and then 1, 0, 1, 1, and then 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. So that's how that would look in binary. And there's a table on page 32 in your book if you want to look it up. It's got all of those listed out, and so you could use that chart if you wanted to kind of see how those numbers relate to one another. In hexadecimal, in binary, each character represents a bit, but in hexadecimal, each character represents half a byte. This is hexadecimal. I should put it there because the other one's there. So hexadecimal. Each character represents half a byte. Now, what is a byte? How many bits? 8 bits. Tell me, anybody? Preston?
Yes.
Okay. So a byte is 8 bits. This is half a byte, so that's 4 bits, or they cleverly call it a nibble, spelled with a Y. So it's byte spelled with a Y. So a nibble is half a byte or 4 bits. And so if you want to, if each character represents half a byte, then to represent a whole byte, I need to use 2 characters, right? So often with hexadecimal, that's what you'll see. You'll see it grouped together as 2 characters at a time. And so you'll have like 2 characters that go from, so you use 2 characters to represent whole byte. And so the characters will go from 00 to FF, which in decimal, that corresponds from 0 to 255 in decimal. So if you have a whole byte in hexadecimal, you can basically represent 256 total numbers. And that's going to be important when we get to the next chapter where we talk about when we start looking at graphics programs and how you represent color in graphics programs. On the web, this used to be the way that we always had to enter into color, was we'd use the hexadecimal representation whenever they first, when the web first started becoming prominent and you started building web pages and you identified like what color you wanted your text to be or something like that, you would do it with this hexadecimal code. You don't necessarily have to now, but that used to be how we did it. All right, so if I want to convert a hexadecimal number to binary, let's look at how we would do that. So let's say we have a hexadecimal number D2E, and I want to convert that to binary. The way that I would do it is just use the table here. That's the easiest way to do it, right? So we've got D, which we know corresponds to 1101, right? And we've got 2, which corresponds to 0010. And we've got E that corresponds to 1110 right here. And I'm done. No math or anything, right? It's just being able to build this table if you're going to be able to convert from hexadecimal to binary. And then you could now that you've converted it to binary, we know how to convert from binary to decimal, so we could go to decimal if we wanted to, right? And that's another way, like in decimal, graphics programs will now let you put this stuff instead of in hex, it'll let you put it in decimal form. And again, we'll talk about that next chapter. All right, what if we want to go from binary to hexadecimal if we want to go the other direction? What if we have 11010 and we want to convert that to hexadecimal? What you want to do first is you want to bust it up into nibbles, right? Take it in nibbles. So 4 bits at a time. And so in order to do that, we're going to have to pad this guy with a couple of zeros. So the first half of it would be 0, 0, 1, and then 1, 0, 1. So everybody see what I did there? I just put enough zeros on the front here so that we, instead of having 5 digits, we had 8, and then we could bust it up into groups of 4. And then I can again just look at my chart and say 0, 0, 1 is 1, and 1, 0, 1, 0 is A. So that would be how I would convert that from binary to hexadecimal. Any questions about that? Yes?
Can you use that enough series to make it groups of 4?
That's exactly right. Yep. We started at 2, is that right? Yeah? Okay. All right, so one more number system we want to talk about that's used in the computer world, and that's the octal number system. And octal numbers sounds like what you would think it would be. What do you think octal numbers is? Base what? 8. Base 8, right? Base 8. So it only uses numbers 0 through 7, and if we were to, let's say we had a number 174, so we see base 8, so it uses numbers 0 through 7. So instead of each number being a power of 2 or a power of 10, like we have in decimal, each place is a power of 8, right? So if we had octal number 174, and we wanted to convert that to decimal, 174, we would do exactly like what we did for binary to decimal. We'd recognize that this is 8 to the 0, this is 8 to the first power, this is 8 squared. And so that corresponds to 1, 8, 64, right? Each time you multiply it times 8. I'm not going to give you a big one of these where we go up to some large number, so this is about as complicated as it gets. And then what we remember, what makes it a little bit harder here, is that in binary, it was just 1 times this number. You know, if I had a 1 here, it was 1 times 8. But here, it's actually 1 times, to convert this to decimal, I have to do 1 times 64, because that's what's in this place. A 7 times 8 here, plus 7 times 8, plus 4 times 1. And so we add all that up, we get 64 plus 56 plus 4. So, what, 124? No? Did I do something wrong? That's right. Right?
That's what I got.
Okay. The answer I have on my notes here is wrong. I have 114 on my notes.
Yeah, it says 114 in the book.
Oh, does it say 114 in the book? Sounds follow the author. He led me astray. Does everybody agree, though, that that's what it should be? I mean, I actually have 64 plus 56 plus 4, which is clearly 124. So, I'm going to write the author, see if I can get some money for that. What page is that on?
35.
Yeah, wow, look at that. Loser. I would never make a mistake like that. Just don't talk about pre-calc class earlier, the first class of the day. It's like one mistake after the other. Okay, let me see. Just want to correct my notes while we're thinking about it. Data. Chronos. Percentages. This is. so here, so any questions about that? Like I said, that's as hard as it's going to get. I'm not going to do anything super complicated with octals. I just want to make sure you understand the process. It's the same as we did with the binary. All right? All right, let's talk about Boolean logic. This is kind of fun, I think, with my weird math brain. Boolean logic. So there's 4 operators that we've got to make sure that we know if we're going to work with Boolean logic. And
How do you spell it?
B-O-O. Sorry, that's not a B. Not Boolean. Not Boolean logic. That's beyond the. You guys wouldn't be able to understand that if we talk about Boolean logic. So we're just going to do Boolean logic in here. All right. Boolean logic. And so branch of algebra where variables can only have 2 values, right? Which makes sense since we're working with computer systems. It's either a 0 or a 1. What's another way to think about 0 or 1? True or false, right? What else?
Binary.
Well, binary, yeah, but what's another? I could say 0 is false and 1 is true. I could say 0 is off, 1 is on, right? Who said that? Oh, you did? I've already got your name up there, right? No? Okay, what's your name?
Aiden.
Aiden. Okay. Wait a minute, Aiden, are you in my other class?
Yes.
I had your name up there. In the other class, that was it. All right, so, are you in pre-calc? You're in geometry. Okay, gotcha. So we're just using 0s or 1s or true and false. And there's 4 operators that we need to be familiar with. They are and, or, not, and XOR. All right, and the book kind of shows some of the different ways that those can be represented, the different symbols that are sometimes used to represent those. And when we start programming, we're going to be particularly interested in the first 3 and talking about JavaScript and how JavaScript represents those. But for this portion of the class, I just want you to be familiar with the word. And so if you see "and" in all capital letters, you know that we're doing an "and" operation. All right. So let's walk through these real quick. What does an "and" mean? The definition of "and" is both sides of the expression must be true in order for the entire expression to be true. So, like in other words, if I tell you that if you give me milk and cookies, I'll be happy, right? And you give me only milk, I'm not going to have a smile about it, right? We're missing the cookies. I wanted milk and, but I didn't say milk or cookies. I said milk and. Yes, Isaiah.
Do other people just not drink milk just straight up and nothing else?
I'm not in the mood for just milk all by itself, okay? I want milk and cookies. So think of "and" like that, right? So to use a biblical example, James says that faith without blank is dead. Does anybody know what the missing word is there?
Grace?
No?
Love.
Good guess, huh?
Love.
Love? No, another good guess, but that's not what he says. He's talking about the outpouring of our faith. I can say I have faith all day, but if I don't show my faith, it's not true living faith. And so he says faith without works is dead. So the biblical example is you got to have faith and works if it's true salvific faith, if it's true saving faith, right? So "and" means both of those have to be true. Now in Boolean logic, what we mean by that is that if I have an expression like this, false and true, what is that going to equal? It equals false, because the definition says that both sides of the expression the things on each side of the and have to both be true in order for the entire expression to be true. That's the only time the entire expression can be true is if both sides are true. Who said false, by the way? Okay. Now I could write that with zeros and ones as well, right? I could say 0 and 1 is going to be 0. Let me do my little slashes so that we make sure we know those are zeros, right? Does everybody understand that? All right, so the only time, if I've got an AND operator, the only time that I can get an answer of true is if I have true and true, right? Both sides of the expression have to be true. Or with ones and zeros, 1 and 1 is the only thing that will equal 1 when I'm working with the AND operator. Does that make sense? Yes?
So false is 0 and true is 1, right?
That's right. Yep. All right, so let's talk about or. Now, if I said, if I get milk or cookies, I'll be happy, then you're welcome to bring me just a glass of milk, Isaiah, and you'll put a smile on my face, right? Because I said or. So with or, only one side of the expression has to be true for the entire expression to be true. All right, only takes one. So then, if I do not false and true, but if I do false or true, then that will equal true. Because one side of the expression was true. That's all it takes. It's just one side to be true for the whole thing to be true. So whereas over here, like if, let's just show it with zeros and ones. If I got 0 and 0, 0 and 1, 1 and 0, 1 and 1. For all of these are 0. I forgot my little slashes. There we go. 0, 0, 0, 1. Now only that last one there is going to be 1, right? Because that's the only one where both sides of the and are true or set to 1. But in the case of or, 0 or 0, 0 or 1. Nope, not 0. 1 or 0. And then 1 or 1. What's 0 or 0? 0. What's 0 or 1? 1, right? Because one side was 1, so only one side to be 1. Same thing here, it's going to be 1. Here it doesn't matter, as long as one of them's 1, it's always going to be 1. So you see how it sort of flips when you're dealing with ands. Only the last example is 1. When you're dealing with ors, only the first one where both of them are zeros, do you get a 0. Who was it that gave me the answer here that this was 1? Who said that? You, what's your name?
Levi.
Levi. Topper? Is that
Yes.
right? Okay. All right, any questions about ors and ands? How that works? All right, let's talk about not. So not's the only one that doesn't require two expressions. There's not two sides when you're using that operator, it's just one. And it just simply means, reverse the expression. All right, when you have a not. So if I do not false, then the answer equals true. I just flip it, right? If I do check this one out. If I do not 0 or 1, and what is that going to do? Boolean logic, just like when you're doing any other kind of math problem, if you've got parentheses in it, work your parentheses first. All right, so when we start programming, that's going to be important. If I want to force the computer to evaluate my expression in a certain order, then I use parentheses to do that, right? And so what this is saying is do your OR Boolean logic problem first, right? Evaluate that expression first. 0 or 1 will yield what? 1, right? 0 or 1 is 1. And so then now I'm doing not 1. And what's not 1 going to be? Well, that's going to be 0, because I take the opposite, the reverse of 1. So make sure you do your parentheses first. All right, let's talk about XOR. Any questions so far? All right. Where do I want to do XOR? Maybe I can do it up here, because it'll be sort of good to leave the other ones on the board while you see XOR. So XOR is 1 and only 1. I don't know why I did the first one spelled out and the second one I'll do it like this. 1 and only 1 side of the expression must be true for the entire expression to be true. So, do you see the distinction here between this and the OR? Right, with the OR, as long as one side of the expression was true, then the whole expression was true. But with XOR, only one side of the expression can be true. Otherwise, the whole thing's false. So if we change this out from this, if we changed all these to XORs, right? Then only these two things in the middle here would be 1, because only one side of the expression can be true in order for the whole thing to be true. So this last one here actually ends up being false. That's kind of the only way that the only one of the XORs that are different from the ORs. Does that make sense to everybody? Yeah. All right, so let's talk about logic gates. Logic gates are basically physical devices. All right, this is the actual hardware part. We've talked about software and hardware. This is the hardware part that actually performs these Boolean logic operations. Okay, so logic gates. Logic gates are physical. That's a physical, I guess a logic gate without the S. A physical device that carries out a logical operation. So it's basically hardware that performs these operations that correspond to the operators that we just looked at. Of course, they're more complicated ones, but these things basically receive, so in other words, they receive Boolean values zeros and ones, or since they're physical devices, really it's on a circuit on or off, right? zeros and ones and return, receive Boolean values and return a Boolean output. So like I said, when you're talking about electrical circuits, when we have a 0, it just means there's no current running through it. When you have a 1, it means that there is current. And so it would be, it's beyond the scope of this class to like talk about how you would actually build a circuit like this. And so what we're going to use is something called abstraction to represent it. And so let me just give you a definition for abstraction. Abstraction is the process of reducing information in detail to focus on relevant concepts. So like in the case of a logic gate, what that means is that I'm not going to tell you how to build one of these guys, right? We're not going to study that. So we're just going to use a symbol here to represent each logic gate, all right? So this is the AND, the symbol that we'll use for the AND logic gate. This is the symbol that we'll use for the OR logic gate. The NOT looks like this. And then the XOR looks like an OR, but it's got an extra line on the back of it here. All right, so we're just going to consider 4 logic gates that do exactly the operations that we just talked about, right, with our Boolean logic operators. And we'll use those symbols. So I should be able to give you a problem, right? If I said, if I had an AND gate, right? And I told you that we were passing in a 0 and a 1, what would be the output of that AND gate?
0.
Be 0, right? Because both of these have to be true. They both have to be 1 in order for it to produce a 1. All right? So what if I did something like this? I did an AND gate, and then I had that feed into a NOT gate. Now what would my answer be? 1, right? So because this 0 and 1 together produces a 0 here, but then when we NOT that, we get a 1. So 1 would be our output. Make sense? So you kind of chain these together, and build more complex logical operations. All right, so let's do, usually if I give you a logic gate problem, I'm going to ask you to build a truth table. And so a truth table, use truth tables to show all possible inputs and outputs for a particular Boolean expression. All right. So, for this one, let's just do a simple one first. We've got this XOR gate. And we've got input A and input B. And the result is going to be output R. Right? And I say write a truth table for that. And you could say Well, this is actually the Boolean logic problem that's being expression here is R equals A XOR B. Right? Everybody agree with that? Since that's my logic gate for XOR, we're XORing together A and B to get a value R. All right, so let's build our truth table. And so it just looks like a table. At the top here, we've got input A, we've got input B, and then output R, right? And in this case here, the number of possibilities is just going to be 4. 1, 2, 3, 4. So I drew my table a little large. And that's just because the values can only be 0 or 1, or true and false. We'll do this one true and false, and then the next problem we'll do 0 and 1. All right? So the possibilities here are A and B can both be false, or A can be false and B can be true, or A can be true and B can be false, or finally true, true. Right? Those are all of our options. And so in the case of XOR, what does XOR say again? XOR will be true when what is the case? Yes?
XOR is true when only one side of the expression must be true.
That's right. Only one side, right, is true. So the only times that we're going to get a true is these two scenarios here. So these are our trues, and these would be our falses. Make sense? If I ask you to write a truth table for that, you guys think you can do it? So like on the next quiz, I've asked you to write a truth table? Yeah? All right. Cool. So let's do a little more complicated problem. And now we're going to put 3 gates together. So I've got this one here with an input A and B, and we're going to feed those to this gate and have an add input C there, and then those are going to go into this gate, and finally we're going to have our output R. Right, so this table is going to have to be a little bigger because now we don't just have 2 inputs, we've got 3. So we've got A, B, C, R. And the easiest way to do this is just write down all of your possible input values first. And I'm not sure how many rows we need yet. So it's going to be the possible input values. I'm going to do zeros this time, just so it'll be a little easier to write. So I'm not even thinking about the problem yet. All I'm having to think about is what are the possible inputs, because I know they can each be 0 or 1. So I'm just going to go through the list and do all of those. So we should have had 8 rows. So does everybody agree as I wrote that down that those are the only possibilities for our inputs? Have we left anything out? It's every combination with 3 inputs. And the way that we know, yes?
Does it matter what order they're in?
It doesn't matter. No, it's just, to me, it's easier to make sure I don't leave something out if I do it that way. But I'll know that I got the right number of rows because remember, there's only 2 possible values for each one, 0 or 1. And how many inputs do I have? I have 3. So 2 to the 3rd power is 8. So I should have the number of rows that match 2 to however many, the power of however many inputs I had. If I'd stuck another gate in here and had like a D in there as well as a possible input, then it'd be 2 to the 4th power, 16 rows that I would have to have, right? Don't worry, I won't give you one of those on the front. All right, so let's think through each of these and make sure that we understand what we're doing here. So, A and B, we AND together A and B in our first one. And when you AND 0 and 0 together, what do you get? You get 0, right? In our first row, C is also 0. So when I OR, right, this is AND, this is OR, and this is NOT. So when I OR 0 and 0 together, I get a 0 here. But when I NOT that 0, I get a 1, right? So this is going to be a 1.
Isn't the first one OR?
No, well, if it is, it's just my draw line's bad. This is rounded, and this one comes to a point. That's what it's supposed to look like. All right, so there. Right? Isn't the point, the one that comes to the point is the OR? Right? Is that right? Okay. All right, so if we do the same thing again, right, the second row, we've got 0 as the A and B's are zeros, but now the C is going to have an input of 1. Well, 0 and 1 together gives you 1. And then when we NOT that, we get a 0. So this value is going to be 0. So you're going to have to do that and go through each one and think through it, right? And you could write this out if you wanted to. It might be easier for you to see if you wrote it out like this, but it's just sometimes it can be kind of hard to write this out to make sure you're doing it in the correct order. I just have to make sure I put my parentheses in the correct place, right? So if I write it like that, that's really what it would be written out in Boolean logic. The first thing I have to do is my innermost parentheses, which is and the A and the B together, right here. And then I have to OR whatever the result is of that with C. That's what's going on right here with this OR gate. And then finally, that whole expression, I have to NOT it. So if we went through each of those, it's at some point you should be able to get to the point where you go A and B, 0 and 1, that's going to be 0. 0 OR together with a 0 is going to be 0. And so when I NOT that, it's going to be 1. So this is going to be 1 right here. A and B, 0 and 1, ANDed together, still going to be 0. But OR that with a C, that's going to be 1. And when I NOT my 1, I'm going to get 0 here. And just kind of be able to go through those and get the correct answer. So if we did the rest of them, we should get this right here. And so I'll sort of leave that to you as an exercise to make sure that you can get those, that logic makes sense to you as you go through that process. But any questions overall on how you would build a truth table and how Boolean logic works? No? I can tell you got a burning question, Caden. What is it? Come on, ask me. It's okay. I know it all. Not just computer science. Ask me any question. That was your chance to stump the teacher and get your name on the board, because I don't really know everything. That was just a joke. But I did. My nephew used to say that Uncle Jamie knew everything in the whole wide world of the United States of America. So that's an actual quote when he was 3 years old. All right, so let me hand out a worksheet. So I've got a worksheet so you can practice this, and then you will be done for the class. But I can't let you guys go yet. We've still got 20 minutes. So if you want to, you could actually go ahead and work on your worksheet now and be ahead of the game. If I can find the worksheet, let's see. Yeah, here it is. By the way, my nephew doesn't think that anymore. Now that he's 22, he knows it better. All right, 1, 2, 3. Actually, he's probably older than that. 25. Right, Noah. Noah.
Isn't he like 30?
Is he 30? Oh, he definitely knows then. I've made plenty of mistakes throughout his life. Poor little kid. He's Hopes and dreams were dashed.
You know your son is 22, right?
Yeah, I'm getting kind of old. Thanks for bringing that up, Joshua. Appreciate that. That's why you never let your kids into your class. All right, so just so you know, for next time, you're going to read the rest of chapter 1, right? And do that worksheet. That's your homework assignment. Read rest chapter 1. Do worksheet. And study for quiz. All right.